Bismillahirrahmanirrahim. Now our next theorem, that is if W is a non-empty subset of the vector space V over the field F, then the is a subspace of V if and only if W is closed under the vector addition and scalar multiplication on of the vector space V over the field F. Proof. Suppose that W is a subspace of the vector space V over the field F, then W is closed under the vector addition and scalar multiplication, that is all the F. W is a subspace of the vector space V over the field F, then the elements of W are the elements of the vector space V, and all the elements of the vector space V satisfy the condition of the vector addition and the scalar multiplication of the vector with the elements of the field. Therefore, these elements are the elements of W, also satisfy the condition of the vector addition and scalar multiplication. To prove the converse of the above theorem, suppose that W is a subset of the vector space V over the field F is closed. W is closed under the vector addition and scalar multiplication, and in this case we suppose that W is closed with respect to the vector addition and scalar multiplication. To prove that W is a subspace of the vector space V over the field F. To prove that W is a subspace of the vector space V over the field F, since the set W, the subset W of the vector space V is closed under the scalar multiplication, therefore for each element of W and minus 1 is a scalar in the field F, since the field F is an additive abelian group, therefore for an element 1 there exists the additive inverse minus 1 in the field, such that 1 plus minus 1 is equal to 0. 0 is a scalar of the field. That is, that means that minus 1 is a scalar element, is a scalar in the field F. Therefore, under the given condition, under the condition of scalar multiplication, the elements of W and minus 1, the operation of the elements of W and minus 1, that is minus 1 multiplied by x is equal to minus x, is contained in W under the given condition which we have to suppose in this case. That is for each element of W, the inverse of each element of W is exists in W. Thus the additive inverse of each element of W is in W. And to check the second condition, that is if W is closed under vector addition, to check the second condition, that is W is closed under the vector addition, that is for each element of W, the inverse of each element of W is in W. The element the additive inverse of x is minus x is contained in W, such that under the given condition, that is the vector addition of the elements of W, the result of these two elements, the additive inverse of these are the additive inverse of each other. Therefore, the addition of these two elements gives the additive identity element. This result must contain in W according to our supposition, that is the vector addition of the elements of W is in W. So these two elements are the elements of W, and when we add these two elements, the result must contain in W. That is, the additive identity of the vector space V over the field F is also contained in the subset W of the vector space V. That is, the additive identity of V is in W. Now, to check the next condition, that is since the elements of W are the elements of the vector space V. Now since W, the set W is a subset of the vector space V, therefore each element of W are the elements of the vector space V over the field F. Therefore commutative and associative laws hold in W, hold in the elements of W. So this condition is already satisfied. According to these condition, these are two condition. These two condition with these condition, we can decide that the set W, which is the subset of the vector space V over the field F with respect to the addition, is an abelian or commutative group. The remaining properties of the vector space is also hold in the set W, because these elements are the elements of the vector space V over the field F. Hence, we can decide that the subset W is a subspace of the vector space V over the field F.